Our next presenter is a CERIAS postdoc. Washim Mondal is a postdoc student in a dual in industrial engineering and civil engineering. Yet again, the example that CERIAS is truly an interdisciplinary education and research institute. And his academic advisor or faculty advisor that he is embedded in the lab, I recently got to know. And Satish had told me, said, well, I've been meaning to reach out to you for a couple of years now because I'm venturing more and more into security, especially in critical infrastructure. Yeah. And it looks like we're going to be writing a proposal together this spring and summer on autonomous and connected vehicles. So, Dijin, this might be something that we'll want to talk to you about as well. Yeah, so it's exciting to see this. And civil engineering was one of those departments that we didn't have anybody embedded in us, but we do now. So, Washim, welcome. Thanks. We're excited to hear about your research.
Thanks. Is it audible to everyone?
Sounds good.
Okay. Oh, thanks for the kind introduction. So, I'm, as you have heard, I'm Washim Mondal. So, I'm a postdoctoral researcher at civil engineering, and I'm also affiliated with industrial engineering as well. So, I'm working with Professor Satish Ukkusuri for last 1 year, and as a postdoctoral researcher. So, this presentation was supposed to be delivered by him, but unfortunately, he's not present. So, I'm kind of presenting on behalf of him. So, let's get started because we are kind of already delayed. Okay. So, the topic of my presentation is cyber physical security in intelligent transportation network. Is it being distorted? Yeah. Okay. So, let's say you are moving, you're traveling on a highway, right? And let's say your current position is depicted by in one of these vehicles. And let's say from your current position 5 kilometers down the line, there has been a minor accident which is creating some kind of congestion down the lane or down the road. Now, you are not aware of this particular situation that is happening 5 kilometers down the road, but you are seeing that some of the vehicles are kind of slowing down. You are seeing the effect, but you do not know the cause of this thing. And also assume that from your current position, 1 kilometer down the line, there is a escape route. So, if you take that escape route, you might be able to avoid that kind of congestion that is being created 5 kilometers down the line. But if you take the escape route, you have to travel a longer distance to reach your destination. Now, at this current position, you have two options. Either you can take the original route, you do not change your route, or you can take the escape route and you reach to your destination. But the trade-off is that if you take that escape route, then you have to travel a larger distance. Now, what should you do? So, if your vehicle is not a connected vehicle, if it is just a simple vehicle which is not connected, it is not gathering information from neighbors, then you cannot decide actually because you do not have the full information. But suppose if you are in this particular situation, when different vehicles are connected to each other via short range communication, then the situation could be dramatically different. For example, the vehicle which is present 5 kilometers down the line at the accident spot, that can relay the information to its neighbors, and those neighbors can relay the information to their neighbors, and in this way the information might propagate through this whole network, and within a millisecond or few seconds you might be updated about the situation that is happening down the road. Now, this is one of these situations where then intelligence is emerging out of this network connectivity. This is one of the examples which we define as the intelligent transportation network. So, this kind of network where different vehicles are connected to each other via this short range communication, this kind of network is generally defined as the Internet of Vehicles. So, you might have heard about the Internet of Things, right? So, for example, if in your home different electronic gadgets are connected to each other via the short range communication protocol, then we call this kind of network an Internet of Things or IoT network, right? So, this is similar to an IoT network for the vehicular networks. So, in the US currently almost 50 million or more than 20% of these current vehicles are equipped with different kind of connectivity. So, this connectivity can be of three types. It could be a connectivity to the cloud servers. So, this can be connected via this traditional 4G or 5G communication via the cellular network, and it could be a connection to the nearby different kind of infrastructures. For example, the vehicles could be relaying some kind of information to the nearby traffic controller. They could be relaying some kind of information to the nearby RSU or roadside units, right, which we also call the edge servers. And they can be also be connected, or they can be relaying information to the nearby vehicles as well. So, these three types of communication that might arise. One is vehicle to vehicle, one is the vehicle to information, vehicle to infrastructure, and third is the vehicle to the cloud. So, why this kind of connectivity is required? So, there could be several applications. So, I will be just listing few of them. One could be this cloud assisted fault diagnosis. So, suppose that something has broken down in your vehicle. It is not that serious that you have to stop, but it is certainly a major issue. Now, so if your vehicle is kind of equipped with that kind of communication, so that can generate the logs of these vehicles, and that can be transmitted via different kind of connectivity channels to the cloud servers, right? And the cloud servers can read this log, and that can diagnose what is the fault of this vehicle, and then suggest some kind of remedy for that. That can be done on the fly. You do not have to stop anywhere. You do not have to stop anywhere. And it could be also be very useful for the autonomous driving as well, right? For example, in the autonomous driving, what do? You have different kind of cameras or different kind of sensors equipped in your vehicle, and those kind of informations are perceived by this this autonomous vehicle, and they are processed by different kind of deep learning networks, right? But your vehicle, they might not be equipped with that kind of computation power. So, what you have to do, you have to partially offload some of these inputs or some of this data to the cloud servers. The cloud servers, they are equipped with that kind of computation. They can do different kind of computation and suggest different kind of action strategy for your vehicle. So, for autonomous vehicles, so this kind of communication with the server, that might be a very necessary thing. So, there are other applications as well that I am not going through. So, this particular picture that summarizes the kind of communication that you are talking about. So, in the left, in the right up, you can see there is a picture of the CAV, and that is being connected to different other CAVs, which is shown in the yellow box below that. And that can also be connected to different kind of this traffic controllers, which are the common traffic lights that could be equipped with different kind of computation power. And those vehicles, they might also be connected to different kind of roadside units as well. So, that might act as a different kind of edge servers. And those traffic controllers and those edge servers, they themselves might be connected to different kind of cloud servers as well. So, you might be able to directly connect to the servers via this 4G or 5G communication, and you can also connect to the servers via these roadside infrastructures as well. So, this is the summarization, and this particular picture shows that what kind of instruments are generally being different connected vehicles are generally being equipped with. So, in addition to this communication units, right, so those are required for dedicated short range communication. So, these connected vehicles, they are generally equipped with different kind of cameras for perception of the nearby roads, and they could be equipped with different kind of lidars or different kind of radars unit. So, lidars and the radars, they will be required. What they do is they basically transmit different kind of radio signals, and if those radio signals are getting reflected back by different kind of obstacle, then by analyzing the reflected waves, you can basically say that if there is a certain kind of obstacle nearby, and if there is an obstacle, then how much, what is the distance between your vehicle and that particular obstacle. So, this basically is a summarization of different kind of instruments that the ECVs are equipped with. So, until now, so we have been talking about different modes of communication. Now, we can talk about what are the contents of different kinds of communication that is happening in this vehicular network. So, for example, if you look at this V2V or V2I type of communication, then one of the basic kind of communication is of the communication of basic safety messages, right. So, for example, that can include different kind of locations, the location, speed, and the heading information, the trajectory information of that vehicle, and that might be broadcasted to nearby vehicles or to the roadside infrastructure units for further processing or coming up with a traffic signal plan. And these are generally transmitted 10 times per second. Now, if you look at the vehicle to cloud type of communication, there can be two types of communication. One could be transportation related communication, one could be non-transportation related communication. So, for example, an example of non-transportation type of communication is if you want to fetch the weather report data. So, that is non-transportation type of communication. And if you talk about the transportation related communication, that could be the road congestion network, right. So, if you want to visualize the whole, what is the situation of the congestion in the whole network, then you have to fetch that data from the cloud. And for example, there could be, if you want to plan your route accordingly, then you have to do that kind of calculation in the cloud, because vehicles they are generally not equipped with that kind of computation power. So, and thus this we talked about vehicle to cloud, and now let's talk about infrastructure to cloud. This infrastructure to cloud, as you've already mentioned, it could be transmitting different sorts of information. For example, what is the current situation of congestion situation in that particular network or that particular intersection? How many number of connected vehicles are there? How many number of non-connected vehicles are there? Or what is the current signal phase at that particular intersection? All these kinds of information that might be transmitted from infrastructure to the cloud. So this is again a summarization of different kind of services or different kind of activities that we are talking about. So you can see that this cloud infrastructure that is connected to different vehicles via this vehicle to cloud communication, and this cloud infrastructure that could be connected to different nearby roadside units, different traffic controllers as well. So these clouds, they basically serve three different kinds of services. One could be your infrastructure as a service. Another could be your platform as a service, another could be the software as a service. So what does it mean? So for example, if you want to just store some amount of data in the cloud, right? You do not want to do anything else with that. So that could be an example of infrastructure as a service. So you're just using the cloud as an infrastructure. And if you want to perform some kind of manipulation on the data on top of that, then that could be an example of platform as a service, right? And and another kind of service that is provided is software as a service. So for example, if you want to fetch your route planning, so that kind of computation has to happen in the cloud, and then that output is downloaded in the vehicle, right? So those kind of services that is provided by different kind of softwares. So that is another type of services that is provided by the cloud. So this is an summarization of, again, the scenario that you're talking about. Different vehicles are connected to each other. Vehicles are connected to infrastructure. For example, your traffic controller, and the traffic controllers could be connected to different kind of cloud servers. Now, of course, this kind of situation is desirable because this has many applications that we are now talking about, right? So it is required for route planning, it is required for autonomous driving, it is required for so many other things. But it also raises the questions, right? So if someone gains access to in one of these components and they can control this output of that component, then what will happen? So there is an increasing vulnerability in this vehicular connected networks. And now the question becomes, how do we address these kind of situations? Now, before going into the preventive measures that we can take, so we first have to discuss that what we want this kind of cyber physical security system from. So what are the key features that we should be looking for in this cloud, in this cyber physical vehicular security system? So we mainly will be looking for three key features. There could be other features as well, but I am just listing only three key features. The first feature is the confidentiality or the privacy. So what does it mean? So for example, when you are connected to the cloud, right? So you might want to save several kind of information. For example, your vehicle ID related authentication code, right? So in your vehicle, and you might be willing to, so you have to probably also store different kind of information regarding your vehicles, right? The engine number or probably the owner's name and address, all these kinds of information might be stored in the cloud. Now all these kind of informations are kind of sensitive data, and you do not want to give access to this data to a third malicious party, right? So this is, so when you can ensure that no third party or no malicious agent can get access to those kind of data, then we call that a confidential proof or privacy proof system. And the second aspect is the integrity. So if you're generating some data, then the system should ensure that that data is not changed, right? For example, if you are, let's say, if you're generating a route plan, right? So if you're giving input, some input, you are saying that I want to go from point A to point B, and you are transmitting that kind of information to the cloud. And in the meantime, during when that communication happens, so someone or some third malicious party that they are getting access to that kind of information, and they're changing the data on the fly, then what will happen? So the cloud will be seeing something different, right? The cloud might be seeing that, okay, you want to go from point A to point C, not from point A to point B. So if these kind of changes are happening, so different kind of problems might be arising. So for example, one of the effect could be the congestion in the road network. So people are trying to go somewhere and you are just redirecting them to somewhere else. So this is one problem that might arise. So you want to ensure that the integrity of the data that is ensured. And the third is the availability of the service. So for example, we have talked about this autonomous vehicle, right? So the vehicle, those vehicles are constantly in communication with the cloud infrastructure, and they want to get different kind of informations all the time. because not all the computation can be done in the vehicle itself. They are not equipped with that kind of computation capability. So if those kind of communication is broken down by some methods, for example, you are creating a jamming signal, right? You are transmitting a high powered signal centered at a certain frequency. And in those cases, your vehicle cannot communicate with the nearby roadside unit. So what will happen that you cannot get any information from that roadside unit or from the cloud infrastructure. So in these cases, your whole system might collapse. So these three things, so when we are talking about when you want to design some kind of cyber physical system, we want to ensure that these three key features are ensured. Sorry. Now let's talk about different types of cyber attacks that can happen in the transportation system. So based on the attack, we can segregate the attack in two types. So one could be your attack on the individual vehicle. So vehicles are compromised, and another could be an attack on the whole system level. The whole system is compromised, and based on the consequence of the attack, we can segregate the attack in two types. One could be the active attack, for whose the aftermath of that attack is immediate, and that could be a passive attack for which the aftermath could be delayed for several days, or the malicious agent that could have some other intention to use with the data. So let's take some examples. Let's talk about these vehicle level attacks. So one of the attack could be gaining access to the ECUs. ECUs is basically electrical control units, right? So for example, there could be some automated units which are controlling the RPM of this your engine. That could be controlling your steering in the autonomous vehicle, right? If someone is getting access to those kind of control units, that can create a havoc, right? And there could be other kinds of attack. For example, someone getting access to the sensors data, right? So they can actually deactivate the sensors or can feed false information to the sensors. That could be very dangerous. And so, for example, if there is a bend and somehow someone getting access to the sensors and saying that there is no bend, then you go and hit the fence there, right? So those different kinds of consequences might arise. Another thing could be broadcasting certain messages to create illicit reaction of the vehicles. For example, if someone if there is a broadcasting message that says that okay, there has been an accident just few meters down the road, then you will be just creating a very high intensity break, and that might have some consequences as well. And we also talked about this man in the middle attack. So man in the middle is basically you have one agent which is transmitting some information, and there is another agent which is receiving some information, and the middle there is a third agent which is basically receiving those transmitted information and changing something, and then again retransmitting to the your receiver. So this is basically called the man in the middle attack, and that can happen in a vehicle to infrastructure type of communication, or vehicle to cloud type of communication, all those things. So, and another is just eavesdropping, which is basically a passive attack. Your immediate consequences kind of delayed, so there is no immediate consequence, but the malicious agent, they could be collecting different kinds of information, the information about your routes, information about the name of the owners, the address of the owners, all those kinds of sensitive information that we collected. Now let's talk about the system level attacks. So one of this could be the denial of the service attacks. So we are talking about this attack a few minutes before. So in this case, what happens is that so certain amount of bandwidth is allocated, right, for this vehicle to infrastructure type of communication. Now if you by some means can flood that bandwidth, right, then if you flood that bandwidth, then the receiver they cannot actually decode that what is being actually the intended message, or what is actually being transmitted from the vehicle to the infrastructure, or from the infrastructure to the vehicle. So all these different kinds of sorts of scenarios might happen. Another thing could be the generating incorrect commands, right? So so the example that you have also talked about. So let's say someone is getting access to the traffic controller. It is generating the signal plan in a way that is not an optimal solution, or it is not trying to minimize the queue length, or it is not trying to minimize the delay of that vehicles or waiting time of the vehicles. So in these cases, what might happen is that there might be large congestion in the vehicular network. So this generating incorrect commands from the controller, that could be a problematic scenario. So, and passive attack is of course this collecting different kind of operational information from the infrastructure, right? So for example, it could collect that what are the statistics of the vehicle arrival at a certain infrastructure for maybe some future uses. So that can be exploited to attack different kind of vulnerabilities of this different infrastructure. And there another is this Cybel attack. So basically they create multiple identities, fake identities, to create a, for example, a what do you call that, a false queue, right? So there is no queue, and there basically controllers is perceiving that there is some queue. So in this case, there you are kind of indirectly forcing that kind of infrastructure to take different actions that are not intended. Now, those are the different kind of attacks that might happen in the vehicular network, right? And what are the consequences of that? So we want to come up with a system or an infrastructure or a vehicular network in which those kind of attacks have minimal consequences. So you want to design something in which even if there is some kind of an attack, then the aftermath of that attack is not that much consequential. That is your target, and that's how you want to design your whole system. But the question now is, how do you design those kind of situations, and what kind of measures that you should target? So one of the idea is that you want to make the network as resilient as possible. Now the question now immediately becomes that, what is network resilience? So the network resilience is the ability to resume functionality even in the face of catastrophic failure of some of its nodes, right? So you have a network which consists of different kind of nodes, and those nodes are connected to each other via different edges, right? And suppose an attack happens, then some of the nodes will be malfunctioning. For example, if you take an access to the vehicle, then those vehicle might be malfunctioning, or if you take an access of certain traffic controller, those traffic controller might be malfunctioning, and there could be attack on the edges as well. So for example, your vehicle is trying to communicate with the infrastructure, so you can gain access to this communication channel, and you can actually either by jamming, you can just completely disrupt that communication channel, or via this man in the middle attack, you can change the content of this communication channel, right? So all sorts of things might happen, and your network might change as a result of this attack. Now the question therefore becomes that, how do you make sure that even if all these things happens, so even if all these things happens, and in the aftermath of those events, if your network can perform the duty that it was supposed to do, then you can say that your network is kind of a resilient network. That means that attack does not change the network functionality that much. So for example, let's take this example, right? So it's a very simplistic description of a network. So in this case, we have 5 outer edges, 5 outer nodes, and 1 central node, right? And all of these outer nodes that are connected to only through this central node. So for example, you can take it to be a very simplistic computer network. So your internet is basically a computer network, so millions and billions of devices are connected to each other, and you can just take it as a very simplistic description of an internet, so which maybe you are just creating in your own university or in your own department, let's say. So in this case, all of these nodes, they can connect to each other, but they have to go through the central node, right? So this kind of situation that exists. So now let's say what happens, let's say there is a third party or malicious party, he gains access to the central node, right? So he might say that I won't give you any access through this particular node. So this is kind of a denial of service attack. Then what will happen? In all these outer edges, they cannot connect to each other. It is not possible because all of them are just going through only single node. Now let's take another example, right? So in this case, what happens? This is the same kind of architecture that we are talking about, but with some additional details or some additional changes. So in this case, all of these outer edges, they are also connected to the central node, but additionally there is some outer edges as well. So this outer, so even if, so let's say if there is a third malicious party which is getting access to the central node and is basically creating a DOS type of attack, then this central node that cannot be accessed, but still the outer edges, they can actually connect to each other via these additional edges that I have created. So what are the lessons from this kind of example? So one of the lessons is that your resilience, that is a function of where the attack happens, the particular area where the attack happens, that matters. And another lesson is that your network structure, that heavily influences the resilience of the network. So in the previous case, the network structure was this thing, and in this case, our network structure is this thing, right? So we can see that just by changing the network structure, we can make some network to be heavily resilient, or we can make it less resilient. So it is generally the principle that if you add some redundancy in the network, that is not going to hurt your resilience, because, okay. Now this is the, so the example that we gave, so that is a kind of a network where only the structure of the network matters, not the functionality, for example. So, but in the vehicular network, the scenario is kind of slightly different. So why is that case? So in the previous example, only the network connections, that were the only thing that mattered to us. But when you talk about, let's say, a vehicular network, then only talking about different roads and those connectivity, that is not going to be the end of the story. So, we have to, in addition to the physical state of the network, that means how different nodes of this network are connected to each other. For example, those connections could be connection via different roads, different bridges and all those things, right. In addition to those things, we have to also talk about the functional state of the whole network. What is the traffic density at a particular, let's say, particular road, and how it is going to change, what is the pattern and which pattern does this traffic evolution follow, how does it evolve with time, and all those questions that you should take into account, right. So, for example, if you just look at only one snapshot of a traffic network, then you might see that there is only a very limited amount of traffic connectivity at a certain road, but that might change drastically after a few hours. So, all these things, all this time evolution and everything that you have to take into account while considering the resilience of the vehicular network. So, that is a very complicated problem. So, we have an, of course, we have an physical infrastructure, the connection via different roads, those are connecting different, let's say, intersections, that we have. But on top of that, we also have to take into account the functional states and their evolution with time while considering the resilience of the network, right. So, so now the question therefore becomes, right. So, how do we quantitatively describe the traffic flow evolution within a given network? So, let us say we have a connection network that is given, and how the traffic arrivals happen at different external nodes, that is given. Now, can we say that how will it evolve with time and all those things? So, that is the first question that we should answer, because if we cannot answer this question, then we do not know how the traffic throughout this network is going to evolve with time. The second is that if certain links are, let us say, disrupted, right, some of the roads are being congested or something is happening, someone is taking some kind of a malicious, doing some kind of malicious attack on some kind of in some of the vehicles or some of the infrastructures, then how this traffic flow will be changing with time? Will it be drastically different? Will it be very similar? How it will depend on the network structure? So, those are the questions that we have to answer again. And sorry. Okay. Sorry. So, and the second thing is how failure in one link impacts the neighbor. So, suppose this is a connected network, right? So, one road is connected to others, a vehicle which is following through one node, that is going to impact what is happening in the neighbor nodes, right. So, if a failure happens at certain network or a certain part of the network, then how it is going to evolve throughout this, how it is going to spread throughout this whole network, that is the question that you also have to answer. So, now once we understand this whole process, right. So, first thing is that how the network evolves in a natural network. Second thing is if certain kind of attack happens or some kind of failure happens at the network, then how this traffic flow is going to change. And once we understand all of these things, then the next question is now what, so we can take certain kind of measures, right, to prevent this kind of attacks. Now, those kind of preventive measures are kind of not, they are kind of costly measures. So, if you have a certain budget constraint, then you have to judiciously choose the why do you want to put those kind of preventive measures in the whole network. You do not want to uniformly put everywhere, right, because not every node and not every road network is equally important. So, that is the last question that we should answer. So, in this regard, so I will like to go through one particular paper by Professor Ukkusuri, and which was done in 2017, and so that paper kind of tries to address this question. So, in this paper, so they have taken data from the Beijing and the Shanghai, this road traffic network, and they have so they model this whole network via something which is called the dual graph model. So, in the general graph model, in the normal graph model, what happens is that you model each of the intersection as a node and each of the road as an edge that connects different nodes. But in this dual graph model, they model each of this road as a node or a dual node, and different kind of intersections as an dual edge. So, it is kind of a dual representation. So, what was node in the normal graph, that is being transformed in as a edge, and what was edge, that is being transformed as a node. So, there are, so if for example, in this particular figure you can see that this figure A is a representation in the normal graph or the ordinary graph, and the representation is the B is dual transform. Now, if something happens in this particular edge or road section HE, then in the normal graph you will be just showing as a removed edge, right, and nothing changes. But in the dual representation, this road that is denoted by 2, this road 2, so that will be kind of split by two what you call that, 2 sections or 2 sub roads. So in the dual representation, that road was represented by a node. Now, when that particular link breaks, HE link breaks, then you basically say that that node that was representing the road 2, that is being split. So that is the idea behind this vertex split. Now, what do we do, and why do not just use the normal graph representation? So it turns out that if you just transform this whole network into this dual representation, then several kinds of advantages might be achieved. So for example, the different kind of behaviors that we see in the complex network, so that basically arises. So for example, in the complex network, we see that this degree distribution of different nodes in the network, so that follows power law distribution. So same kind of thing also we observe when you transform the whole network into a dual representation. And and if you also observe the vertex split, right, so how the different vertices are split. And so for example, if you have this nodes with certain degree k, and after the split it has been split with nodes of degree I and nodes of degree k minus I, then that division that can be adequately represented by a beta distribution. So these are certain different kinds of features that arises if you just transform the whole network into the dual representation. And the recovery time, right? So let's say one particular road has been removed, and after some time it is being recovered, right? Because the traffic is the congestion is being removed. So what is the time from when the congestion starts to when the congestion is actually removed? That time distribution is adequately represented by exponential distribution. So all these different kinds of advantages that we might see here. So based on this different empirical observation, right, the different kind of fitted distribution that we observe. So the Professor Ukkusuri and his student, they came up with a very nice numerical model that can actually predict that how the traffic flow is going to evolve with time. So they are not exactly predicting the traffic flow, but rather how the degree distribution of different nodes that is going to evolve with time. So they came up with a model. And that model that basically predicts how those things are going to change with time as a function of the traffic load in the whole network. So this is one result that I have taken from that paper. So it basically shows the traffic distribution at certain time instance in the city of Beijing. And this red edges, they are basically showing the edges where the traffic is very slow. This you can kind of describe them as a edge which is not connected edges. And correspondingly, you can see that how the degree distribution is obtained. And this degree distribution is a kind of time average degree distribution for the whole network, right? So they have obtained some. This is this red line that you can see here. This is the time evolution of the number of dual vertices, right? So the number of vertices that is present in this whole network. So if a vertex is split, so you are creating one additional vertices. So if you count the number of vertices in this road network as a function of time, the red is the observed one, and this blue and the skies, these are the predicted one from that model. So you can see that is very closely represented. So further model, so what you can do, so this particular model that we talked about, they basically deal with the time evolution of a particular network as a function of time. But so these are not like disruptive changes, right? So it is not like someone has attacked. So basically they are, in this model, they are trying to predict if certain heavy congestion appears, then what might be the corresponding scenarios. But they are not treating situations where there could be a malicious attack from the third party. Now the question becomes, how do you model those kind of situations? Will it be, will this model be adequate to represent those kind of scenarios, or we have to come up with something else to represent that? So, and finally, once we understand, so this is the part where you are trying to understand how the whole traffic thing is evolving with time, how the network is changing with time, and all those stuff, right? And finally, we have to, once you understand that adequately, accurately, then we have to come up with different kind of interdiction methods. So, for example, this conventional cryptographic or security methods, that might be challenging here, because one thing is that we have limited computational capability in the vehicles, and some kind of computation capability might be required to perform this kind of cryptographic applications. And second thing is that there is a limited bandwidth, so you do not have unlimited bandwidth to communicate from the vehicle to the infrastructure or from the infrastructure to the vehicle. And third is that this is a highly mobile environment. So let's say you are moving with some speed, like say 100 miles per hour, something like that. And so there is a certain RSU that is present at the side of the node. So once you get into that, the coverage area of that RSU, you have to connect to that RSU, you have to authenticate, and all the stuff will happen. And by that time, so you are moving at a very fast speed, right? So this coverage cannot be very large. So you'll be getting a very short amount of time to communicate with that particular RSU. So all of these things, your communication, authentication, cryptography, everything has to happen with this short span of time. Now this is a very challenging situation, and it could be challenging as well because in the physical layers scenario, right? So wireless communication has different layers of communication. You start with the physical layer. In the physical layer, you have to first estimate what is the channel gain of this particular communication channel from the vehicle to infrastructure, and that will take some time. And if your environment is very highly mobile, then what you have estimated at certain point of time, that might not be valid if certain time elapses. So all these kind of scenarios might happen. And then of course there is a low latency for critical messages, right? So this makes the conventional cryptography a very challenging tool to address these situations. And so, and another approach is that we can use different kind of AI or machine learning type of techniques to identify unusual activity in the vehicle level. So we can use the machine learning algorithm to detect if something is out of ordinary. It is supposed to happen, but it is not happening, or that person drives to that particular point, but he is not driving at that particular to that particular point, or maybe something unusual is happening. He is accelerating too much or doing something very peculiar. So all those kind of anomalies that might be detected by the AI machine learning type of techniques. So several kind of algorithms have already been deployed, and several critical and non-critical components that might be detached. So that might give us some resilience, and also by imposing some certain law and resolution, we might enforce certain security measures. And finally, as we have already discussed, adding redundancy in the network, that might also enhance our resilience. So another thing is that, so let's say we know that how to go about increasing the resilience of the network, but the attacker, he might also know the situations. So if you impose certain kind of preventive measures at certain point in this network, then attacker might also see that, okay, so they have imposed this kind of resources, or they have deployed this kind of resources at this point, then I will just target on some other point, right? So that might also happen. So if you decide something to do, the attacker might decide to do something else, right? So this is a kind of a scenario which is generally described by this game theory. So there are certain papers who are trying to address this kind of problem, where the attacker is kind of dynamically targeting based on the available information that what to attack. But this is also a very hard problem to solve. So partially because all the models that are available in the current literature, they do not address the lack of information, right? So they just assume that everybody has the full information, and only in those cases they are kind of solving this problem, but they are not trying to address the real problem that might arise in the real network. So with this, just I would like to conclude with the goals, then what we should do and what basically Professor Ukkusuri is trying to achieve in this particular regime. So how, first of all, understanding how the cascading occurs in response of different attacks. So you have a traffic evolution equation in the normal network. Now if something, if someone is trying to attack different parts of this network, then how this evolution is changing. So that is the first part of this equation. Second is how to distribute. So once you understand that how this whole thing is happening, then you have to judiciously decide where to put your resources. So, and while you will be doing that, you also have to consider the different strategic profile that the attacker might take. So with this, I would like to summarize, I would like to conclude, and thank you for listening.
Thank you, Washim.